So what we have, the Fourier series of x is, I'm going to try and write that as a capital X. There we go. Fourier series of x is equal to a coefficient, a of 0, that is divided by 2, plus a summation. And we use in as our term because we want to use integers, so it's just a good way to remember it. I'm sure there's a real math reason, but that's why I think of it that way. And then we're going to have capital A of n times cosine of n pi x over L, and then that's going to be added to a b of n coefficient of sine with the same interior, so n pi x over L. Now our a of 0 is a coefficient term that we actually have to do another calculation to solve. So this a of 0 is actually going to be 1 divided by our, I'm going to be using L, so we're going to use L, and then that's the integral from negative L to L of the function. This one's not too bad, right? Nice and easy. Now keep in mind that L is, if you have some function like this, and it's defined from, for example, you're wanting to solve it from negative pi to pi, even though your period is 2 pi, L is equal to half that. So that's something people mess up a lot, so you just got to be careful. Okay, so now our next coefficient is a of n. A sub n is equal to 1 over L, and the integral from negative L to L of the function, the little f function, times, I think it's cosine first. I'll double check that here in 2 seconds. Pretty sure it's cosine first. N pi x over L dx. And then b of n is going to look very similar, 1 over L, integral negative L to L of little f of x, which is your function, times sine of n pi x over L dx. So that's the Fourier series, and you can immediately see why people don't like it and struggle with it, and it is easy to make mistakes. So we're going to do 2 different functions here. One is going to be, well, they're both going to have ways to simplify just a little bit, and we'll talk about those as we do them, and then we'll check our simplification on one of them by doing the entire Fourier series. Just so we do the whole thing, we do one of the simplifications and the other simplification. So let's start. I have 2 functions that I wrote down earlier so I could remember them. We'll start with what I think is the easier one, and we'll do the function defined as a piecewise function that is equal to negative 2 between 0 and pi, and then it's equal to 2, positive 2, between pi and 0. Okay? So pi less than x, negative pi less than x, less than 0. There we go. That's what I want. So that's our function that we've defined. So everywhere we see little f of x, we're going to plug in this function. Okie doke. So there's some things we need to figure out real quick before we start. So we know that this function is defined as positive 2 up to 0, and this is my x-axis. And then we know it's defined as negative 2 from 0 to pi. So we'll call that pi, we'll call that negative pi. It's okay if it's not perfect, this is just for our visual. So what's interesting about this, if we kind of notice, we have a definition about functions that are symmetric. We have 2 definitions that are important. We have one definition that's even, where they're symmetric about y. And then we have another function where it's odd, where it's symmetric about the origin. Now, it's really important to think about these things when you're doing this Fourier series, because it can really simplify your life quite a bit. This one doesn't look like what we're used to seeing as a odd function, because we're used to seeing something like, I don't know, like sine, right? Where sine kind of goes like this. That's what we're used to seeing. We know that's odd. But this function here is actually odd as well, and we can prove that by doing the full Fourier and noticing which terms cancel. So we're going to start by doing the short version, and then we'll do the long version. In this case, if I know this is odd, I have an odd function times an odd function. That's even. So when I have an even function from negative to positive of the same number, that becomes 2 times 0 to the positive. So that's fine. B of n will stay. Now if I have an odd times an even, that becomes odd. When you have an odd function from negative to positive of the same number, by definition, those areas will cancel each other, so this will turn to 0. So I'm proposing that this function of this piecewise function that we're working on will cancel an a of n, and I'm also proposing it's going to cancel an a of 0 because this is also just an odd function by itself from negative to positive of the same number. So that's my proposal. So I'm going to say let's just do this b of n term, and then we'll solve a of 0 and a of n and put it all into the Fourier series and see if we're right. So we'll start with, I guess we'll start with a of 0 and a of n just to show that we're doing it right, and then the next one we'll just skip the terms we don't need. Okay, so a sub 0 is going to be equal to 1. Now if we notice, we have negative pi to pi, so our period is equal to 2 pi. But that L is just the 0 to pi part, so that's just pi, right? So everywhere we have an L in all of these, we're going to switch out with pi. So first thing we got, 1 over pi. Integral, negative pi to pi. Then we have a function defined as this piecewise function. So I'm just going to write f of x just for a second, because what we have to do is we have to think about this. How do I deal with this in integration? So a piecewise function in integration, you have to remember that your integral, you can split your bounds. And you can do an integral from a point to a point, and then the other part from the other point to the other point. And you just add them together, as long as the point you're using is in between your bounds. So in this case, 0 is in between negative pi and pi, so I'm going to do the integral from negative pi to 0, which is positive 2 dx, and then I'm going to add that to the integral from 0 to pi, and then that's going to be negative 2 dx. Okay? And so from here, this is a pretty straightforward integral. I am going to factor out the 2 to this pi term real quick, just so I have less things to keep track of. So then this is just going to be an x, so I'm just going to go straight to evaluation. So we get 0 minus negative pi, and then we have plus, well, I'm going to factor this negative out to here, just so I don't lose it, right? And then we have pi minus 0. Okay? And so here we have negative pi is just positive pi, minus positive pi is negative pi. Well, that's 0. So this a of 0 term equals 0. Okay, well that matches what we thought, right? We were saying that that term should cancel, and it looks like it does. Okay. And because of space, I'm going to have to erase these after I do the work and write them off to the side. So we have a sub 0 is equal to 0 in this case. Okay, so let's do a of n next. So a sub n is a little bit tougher. We have a cosine term in there as well that's multiplied. Now I'm going to use the same trick where I split my bounds here, just so that way I don't have to rewrite this 2 times. So we're going to have 1 divided by L. We've already decided our L is going to be pi. And now we're going to write our integrals out. So we have integral from negative pi to 0, because I'm splitting my integral. And then the negative pi to 0 part is this 2. So I have 2 times cosine from this Fourier term here of, and then I have n pi x over, there's an L in there, I know L is pi, so we're going to divide by pi. And then that's dx, and then again we're just going to add here, and then we have 0 to pi. And then we have the same thing, but this one's negative 2. So this is negative 2 cosine of n pi x over pi dx. And big brackets, we don't lose it. Okay, great. Same thing, I'm going to factor out this 2, I'm going to put this negative here, and then I'm going to clean up the inside of these cosines real quick. So we have this equals 2 over pi, and then just keeping the integral there for now, and then we'll evaluate it here in just 2 seconds. Trying not to skip too many steps so people can keep up in case we're a little shaky on our algebra, which is totally okay. Now, oops, sorry, it's not in pi, that's in x. This already looks like, to me, as someone who does a lot of integrals, like this is going to cancel just like we expected. We're just going to go ahead and do it anyways, okay? So, the integral of cosine is going to be positive sine, and that's nx on the inside. Now remember, when you do the integral and there's stuff inside your cosine, you have to take the derivative of that and divide by it. So the derivative of nx is just n, so we're going to divide by n, and then evaluate negative pi to 0. And this 2 over pi is still up front, big bracket, minus here, and then this integral is the exact same, so we know it's just going to be sine of nx over n, evaluated from 0 to pi. Right? Good. So we can already see where this is going. When we plug in 0, sine of 0 is just 0. When we plug in negative pi, sine of negative pi is 0, so this whole thing goes to 0. And then sine of pi is 0, and sine of 0 is 0, so this is 0. So 0 minus 0 is 0, 0 times this is 0, so a of n also equals 0. Okay, so that matched exactly what we expected when we were talking about how this was an odd function. So this is what's known as the sine expansion of the Fourier series. So the sine expansion of the Fourier series is what you do when your function that's going into your Fourier series is odd. And the reason why you do the sine expansion is for exactly what we just saw. When you have an odd function times an even function, you have odd. And when you integrate over negative and positive of the same number on an odd function, you get 0 every time. So with that in mind, we're going to do our b of n real quick, finish solving our Fourier, and then we will do the other function without solving the whole thing, just using a simplification if possible. Okay, so for this one we have b sub n is equal to 1 over pi, because we had an L, we're swapping that out for pi, and then that's the integral. Again, we're splitting our integrals just like we did before. So we have 2 and then sine, and then we already know n pi x over L. When we substitute pi in, it's just going to become nx, so I'm just going to go ahead and skip that step and go straight there. And then we have plus, and then integral from 0 to pi. I guess I need my brackets again so we don't lose our 1 over pi. And then we have negative 2 sine of nx dx here. Okay. So now from here we can factor out our 2 and push our negative out and then do our integral, all in the same step I hope. So I have 2 over pi, and I'm going to integrate sine, which is going to be negative cosine of nx, and take the derivative of the inside and divide by it, so you have an n. We pulled this negative out to here, and then we have negative cosine as well, so I'm going to write another set of brackets, negative cosine of nx, and that's divided by the derivative of the inside, which is just n again. Very good. And then all of that, so we have here evaluated from negative pi to 0, and this one's evaluated from 0 to pi. Good. So I'm going to factor this n out. Since it's distributed across a negative, I only have to factor out 1. So I have equals 2 over n pi. And then this is negative cosine, and this is positive cosine nx. But the insides matter, so we can't just immediately cancel those. That could give you an incorrect answer. So we're going to solve this one out all the way. So let's do negative cosine evaluated at 0 is just going to be negative 1 over, well, we already pulled out the n, so we don't need to do that. So we have negative 1. Okay, and then we have subtracted by, and then negative. So cosine n, where you plug in negative pi, so negative n pi, well, that's not going to just immediately go away. So we're going to have to think about that one a little more. So let's just go ahead and write it. We'll come back to it. Okay? So negative, negative, I am just going to go ahead and write the plus, because those negatives will cancel. And so now we have cosine of n pi, and then subtracted by cosine of 0 is just 1. Okay, negative 1 and negative 1, that's going to be negative 2. So we have equals 2 over n pi times 2. Now we have negative negative cosine is positive cosine, so that's going to be plus cosine of, well, negative n pi, it's actually just n pi because this is even, right? And then we have plus another cosine of n pi, so we can actually say 2 cosine of n pi, right? So that works out really nicely. We can factor out another 2. So now we have 4 over n pi times 1 plus. Now, this is where it's really interesting. There's a simplification here. So Fourier is a series where every n is an integer going to infinity. So every time n is an integer in this particular cosine, so we have cosine of pi, well, that's negative 1. We have cosine of 2 pi is positive 1, cosine of 3 pi is negative 1, positive 1, negative 1, so we have an alternating series. We have an alternating series that is negative 1 to the n. Okay? And that's our b of n term. There's no other simplification we can really do here, so we're just going to leave it like that. So now we have b of n is equal to 4 over n pi times 1 plus negative 1 to the n. That's our b of n term. And boy, oh boy, howdy, I bet you wish we were done. We are not. Okay, so now what we get to do is we get to plug everything into our formula. So we have the Fourier series is equal to a of 0, which we know is 0 in our case. So I'm going to write 0 over 2. And then we have plus the summation from n equals 1 to infinity. Now we know a of n is 0, so I'm going to write the 0, and then I'm going to write still cosine of nx, because we know the pi's are going to cancel, and then I'm going to write the bn term. So now we have bn is 4 over n pi, and then we have 1 plus negative 1 to the nth power times sine of nx. Okay. So we already know this is going to cancel to 0, and we know this is 0, so we now know that the Fourier series is equal to. Now, here's the other cool thing. This summation works just like an integral in a lot of ways, where you can pull constants out, and you can pull functions that don't depend on the variable out. In this case, the variable for the summator is this n. So I can pull out this 4 pi, easy, no problem. This n has to stay, okay? And then, unfortunately, since this whole function of 1 plus negative 1 to the n is multiplied by the sine of nx, I can't really do anything there. So that's the only simplification I can really make. So we have the summation from n equals 1 to infinity of 1 plus negative 1 to the n times sine of nx, all divided by n. And that is the Fourier series that goes with this piecewise function.